Welcome to PyLadies Conference 2023. I'm Ivy, your MC. Now, this sessions we have Ria Bhatia, a driven and passionate software engineer at Goldman Sachs. Over the course of her career, she has worked with various database systems, prioritizing performance, data durability, and scalability. Her expertise extends from cloud-based relations database to embedded persistence key value stores. Ria is passionate about simplifying complex concepts, fostering team learning, and staying at the forefront of technology trends. She is an enthusiastic speaker, having previously presented at prestige conferences like PyCascade and Ribbon Tech Network. Committed to gender diversity in tech, Ria mentors aspiring engineers and has been recognized with the Google Women in Technology Scholarship and the Nutanix Women in Tech Scholarship for her leadership and community contributions. Beyond tech, Ria enjoys screen-free hobbies like reading and embroidery, showcasing her artistic talents. She also adapts at playing multiple instruments, demonstrating her musical talents and diverse interests. Now, if you're tired of waiting for your Python apps to fetch data from the database every time you load it up, you're bored of staring at the screen praying for it to speed up, well, it's time to inject some excitement into your coding life with the power of caching. So Ria is going to bring to you Cache Me If You Can, boosting performance with data caching in Python. Over to you, Ria.
Thank you. Thank you so much for the wonderful opportunity. Thank you to the PyLadies team. I'm so grateful to be here. Again, thanks for the wonderful introduction. I just want to add that I'm somebody who really enjoys understanding the whys and hows of how things work. And I think that makes learning even more fun and insightful for me. So let's straight away get to the main presentation. What to expect. So we learn a lot about caching. We talk a lot about caching. What it is, when does it make sense, how you can implement caching in Python, and finally, I'll share some insights and strategies that you should keep in mind when you're caching your data. And I hope by the end of this presentation, you are not just excited to explore more about caching, but are equally enthusiastic to explore other system design techniques. So let's get started. Starting with the basics. What's a cache? So, it's a bright sunny morning in India right now. It's 10:30 a.m. And if I ask you, hey, what's 25 into 26? You would take some time to calculate the answer, unless you're a mad genius, and then come up with the answer. Hey, it's 650. Great. Now later in the evening, if I ask you the same question, hey, what's 25 into 26? You would rather give me the answer quickly in a single breath. Why? Because now the calculated answer is stored in the short-term memory of your cerebral brain. That's exactly what a cache is. A cache is the short-term memory. It's like a faster accessible location where you can store your frequently accessed data and data which requires redundant recomputation can be stored there. And what it does for you, it optimizes the performance of your application and results in faster load times. Now, before we proceed, it's important to understand what's latency. So latency is the time it takes from the start of the process to the actual execution of that process. Let me give you an example. Suppose you decide to write a beautiful letter to your friend and you use the traditional mail service to deliver it. Now, the time it takes for the letter to reach from the source, that's you, to the destination, that's your friend, represents latency. Now, the more time the postal service takes to deliver your letter, the higher would be the latency. I hope that makes clear what latency is. Moving forward, this is a slide which I think is very important for all developers to understand. On your screen, what you see, the hierarchy of all the storage systems that we have in the computer architecture world. So registers L1, L2, L3 cache, they boast about sub-nanosecond latency, like the data retrieval, data access is very quick. That is because of their design, them being closest to the CPU, and the instructions are fetched at lightning fast speed. The only problem being that the space is limited. And as we move down, we have the RAM, the random access memory, the workspace where all our processes run. Though it still is faster, but it is important to understand the magnitude of difference it creates as we move down the hierarchy from 1.2 12.9 nanoseconds to 120 nanoseconds. Later, we have the secondary storage systems. So you see the time it takes for memory access from RAM versus random disk IO, there's a huge difference. Though RAM has a number of advantages like high read write throughput, low latency. The disadvantage being, firstly, the memory is volatile. Secondly, entire data set cannot fit into the RAM. You need to move on to different storage systems like SSDs or HDDs uh, to be able to persist your data. If you have large amounts of data, and applications do have that, secondary storage is the way to go. Let's keep this in mind and let's move forward. So, for example, you have a beautiful startup, and on your startup, people come, they access images of sunrise, sunsets, and all things wonderful. So, a user comes and requests for an image. Now, all your images are stored in a secondary storage database. So, the server would go fetch it from the DB and send the response back to the client. Now, just imagine this image to be a crowd favorite, a hot selling item, and multiple users are requesting for it. So another user comes in, requests for that image, and again, the server would have to go fetch it from the DB and get the response, return it back to the client. Now you see, if multiple users are requesting for that same image, it just creates a performance bottleneck. We are firstly making a number of network calls to the external database, and it not just puts loads on your database but also takes time, because remember, we just saw that the latency to fetch from secondary storage is even higher than it fetching from RAM. So what we can do is that rather than fetching it from the DB each time, when the first time we fetch it, let's just cache it. Now, cache is the space in the application server's main memory where you store this data. So next time when the user requests for that image, rather than going and fetching it from the DB, the server first checks the cache. If it's present there, that's a cache hit, you return the response at lightning fast speed. So you see, keeping the storage closer to your application server, keeping a memory assigned, you just were able to send the response very quickly. Similarly, now imagine you have a different application that collects some data from the DB and performs some computation. So your user requests for that query, the results are fetched from the database, and this time the server does some complex computation, maybe like finding the aggregate or the average, and then returns the computed response back to the user. Now another user requests for the same query with the same set of parameters. Again, the server would have to go fetch, do the recomputation. Redundant, right? What would have made sense if for the first time we did this resource intensive calculation? Let's just cache it, the request and the response. So the next time a user comes and requests for that, it first checks the cache. If it's a cache hit, that means it's present in the cache, you just return the response. If it's a cache miss, then you go to the DB and fetch the data, calculate the response, and send it back to the user. Summarizing, a suitable candidate for caching would be: one, the function is being frequently called. Second, the output is not changing frequently. Now imagine if that image that we just fetched is continuously changing. There is a chance that if we cached it, we would return stale data to the user. So static data is a more obvious choice for caching. And third one is taking a long time to execute. This is very important. As I discussed earlier, the RAM has limited space and not everything can be present over there. We have to make room for new items. And if your application, for example, fetching something from the database is taking the same amount of time uh, as fetching it from the cache, then we lose the purpose of caching. The function should take a long time to execute and only then be eligible to be cached. Uh, With this, I talk about cache invalidation. As I mentioned that the RAM space is limited, we need to make sure that only items which are being frequently requested or take a long time to execute are present over there. And to make room for something new, something has to get out. So the three strategies that we have is manual, that developers explicitly invalidate the cache. We explicitly choose items that are no longer valid or are outdated in our cache. So I think you must have done that Chrome cache clearing on your own, where you clear your Chrome cache yourself to get rid of all the stale static pages or images that your Chrome might have cached. Second is event driven, that it's a response to a specific event. Maybe something changed in the database and the value is still present in the cache. That also now needs to be invalidated and fresh data needs to be uh, fetch data needs to be included in your cache. Third is time based. That's setting a time limit that after some time your cache expires on its own. And I think this is one of the most popularly used cache invalidation strategies for large scale systems. And with this, now let's get to the fun part, that how do we implement caching in Python? Starting with the easiest way, that's a dictionary. So on your screen, you can see a very simple example where I'm fetching data from an external endpoint API, and you see that every time this particular URL would return me the same amount of data, the same static data. Now, this query right over here, this response, if multiple users are requesting for that information, this soon becomes a bottleneck, because each time we have to send a network call to the remote server and get the static data back. So why not just cache this response? We will cache it by using a Python dictionary. Let's create a dictionary, and the first time you get the response, just cache that, just put it in the dictionary. And when somebody requests for that function again, you just check the cache. If it's present, if there's a cache hit, you return the response. And you see the time difference it creates. The time taken for the actual query without caching is 1.14 seconds. And trust me, it will be more as in when number of people are requesting for that same information. It just puts loads on your remote server. But with cache, it's zero point 0.0 seconds. It's a huge optimization. In today's world, if your application is not fast enough, it doesn't matter how cool it is, right? But the problem over here with this approach is that we don't have a cache invalidation strategy in place. With this, the cache would grow out of bound. Like we will have to implement something so that we can clear the cache. Suppose multiple images are being fetched, not just one endpoint, but multiple data is being accessed. We need to clear that to make room for new data. So I introduced the LRU cache. That is the least recently used cache. I'll explain how that works. And on your screen, you have the classic Fibonacci example. This just reminds me of my data structures and algorithm days. So the Fibonacci example says Fibonacci of n minus 1 plus Fibonacci of n minus 2. So for Fibonacci of 5, the result would be Fibonacci of 4 plus Fibonacci of 3. Now, this is how the recursion tree would look like. This fib of 5 would make functional calls to fib of 4, fib of 3. Fib of 4 will make functional to 3 and 2, 3 to 2 and 1, so forth, and so on and so forth. So first we resolve this side of the recursion tree. That is how it works, because it's basically a stack and the functions are getting added one above the other. Now we have just calculated fib of 2, but as we return, you see over here we have a redundant call. We had just calculated it over here, and we now, since there's no caching in place, we will have to make a functional call again, a redundant operation. Similarly, for fib of 3, you just calculated over here, and now you have to do the same thing over here. Just puts undue load on your function, on your application, and resource intensive operations, which could have been avoided. How? Let's use a cache. So we use a LRU cache decorator and we set the max size to 5. I'll explain in a bit what that means. Now, with the cache in place, let's see how the recursion tree would look like. So the first time we calculate fib of 2, we check if the value is present in the cache. No, then we add it to the cache after calculating it. Similarly, for fib of 3, we check the cache, it's not present, we calculate it. Fib of 4, same thing, check the cache, not there, calculate it. But for this particular call, fib of 2, when we check the cache, we find the value. It's right there. So that redundant call is saved. Similarly, for fib of 3, we again check the cache and we get the value. And for fib of 5, from both sides, the result would come in and we can calculate the response. And you see the difference that it creates. So I calculated fib of 40, and the time it takes without caching is 21 seconds, and with caching is literally 0.0 seconds. So you see, this technique basically is called memoization, where you cache the functional calls so that you don't have to repeatedly run the same function for the same set of parameters. And what you see over here, that max size is equal to 5, that means that when the sixth element comes in, something needs to move out of the cache. How will we decide that? That's the LRU cache, least recently used. So the least recently used item would move out and the new item would come in. The max size would always be 5. Till it reaches 5, it will keep on adding all the elements. But as the sixth element comes, the least recently element would move out. And there could be other cache invalidation strategies as well, like FIFO, first in, first out, least frequently used, most recently used, depending upon the needs of your application. Till now, what we have talked about is all about traditional caching. The cache is very restricted or limited to the size of your device, the RAM size on which you're working. But so what if we have two servers? Now, both will have their own individual cache. That is what we have seen till now. And what if one server goes down? The cache also goes down, right? We don't have access to the application server. We don't have access to the cache. So in such a cases, when you're building large scale applications, distributed applications, using distributed cache is an obvious choice. What you see on your screen is Redis. You could also use memcache, and you see just one block over there, but actually it's a number of instances. Imagine it to be as a large hash map where these are all the keys, and the objects that we are fetching from the database would enter one of these instances. So even if application server goes down, we still have our cache in place and still can reap the benefits of caching of faster access, and frequently used calls could be avoided. We have this in Python, PyMemcache library for memcache, and Redis client could be installed. Just import Redis and you have the Redis client, which can connect to your Redis server and do the job for you. Now, this is very important. We have come to an end. I just want to explain the things that you should keep in mind when you're caching. Firstly, caching specific query results versus entire dataset entirely depends upon the need of your application. Whether you want to cache the entire product catalog or you just want to cache that one name which people are searching multiple times. How you can find out what is being searched? Before that, the memory footprint, because we need to understand that the memory is limited. Only those items should be cached which actually are being frequently called or deserve to be in the cache. Profiling your application is very important. Understanding what block of code is taking time, which is a resource intensive thing, finding out all those queries which are taking time to fetch something from an external source. There are multiple profiling tools in Python like C Profiler, Timeit, Yappy. You can use all of these to profile your application that not just improves its performance, but tells you what you need to cache. Having monitoring and metrics in place, understanding what cache hits you are getting, cache misses you are getting. There are functions in Python to do that, like cache info tells you how many cache hits was your application able to serve. Understanding the database logs, that this was something which people requested multiple times. Why not just cache it? Choosing the right cache invalidation strategy, again, very important for your application. The cache hits are very important to optimize your performance, and the data being in cache is the main thing for that, right? And think about data inconsistencies. Are you okay with serving stale data? Will that create a difference to your users? Yes, no. How are you solving data inconsistencies? If something changes in the source, how would you change that in the cache? All this takes a lot of designing, a lot of trade-offs to be considered, and then only you can come up with the application that actually serves your use case. And no application is one size fit all solution. With this, we come to an end. I thank you all. I hope this session was useful. Please feel free to connect with me if you have any questions or you just want to bond over tech, books, or music. Thank you so much again, and I hope you have a lovely day ahead.
Thank you, Ria. You are right on the dot for the timing. It's such a good time manager. Thank you for sharing such a interesting, and I think it's a very important topic that, like, we need to know how to use the cache for the optimal for our program to run optimally. Yep. Let me see. I don't see any questions coming from the speaker, but Christians give a message saying it's a great talk. It's crucial for about caching mechanism in environment where performance and memory is crucial. Thank you. All right. And thank you very much, Ria. And see you in the next sessions or next
You. Thank
conference.
you so much,
Bye.
everybody. Thank you. Bye bye.